with the example that we've been working on, we see now that there is a pattern, there is a behavior with the 6 months autocorrelation value with the latitude. So now a machine learning model can exploit this behavior. However, what is this behavior? What type of functionality does it look like? Generally speaking, it's nonlinear, right? We see nonlinear behavior. So if we were to use a simpler model like linear regression, then it's going to do a poor job. And you might say, well, we can just go ahead and use a more complicated model, a model that's more adaptive to the data, that can learn more patterns, more behaviors. Yes, that is true. We can go ahead and use a more complicated model. But remember that a nice thing about simpler models, that simpler models are easier to work with and easier to understand how they work, to derive insight from them. They're less of black boxes compared to more complicated models. So if you wanted to use linear regression for this problem here, to predict this 6 months autocorrelation value with respect to latitude, then we need some sort of transformation with our feature. Now by visualizing what we have here, what do you guys recommend? What are some recommendations we can do with our data such that a linear regressor can do a better job to find the patterns, to fit a line through the data? What are your suggestions? Well, roughly speaking, it appears to be somewhat exponential. So we can go ahead and transform our data that way. Well, first let's go ahead and see how well our data, how well a linear regressor would do with what we currently have. As we anticipate, it's going to do a poor job to fit a line through the data. But we see that there is some exponential behavior, so let's apply a transformation. So we can generate a feature called u, which is going to be equal to e to the negative x over lambda. Lambda is just some scaling parameter. So let's apply that transformation. So by applying that transformation, then we can go ahead and use linear regression. So essentially what we're doing here is that since the behavior, it's imposed this form, something like this, then I can go ahead and just call this right here as my variable. Call it x1. Let's do that transformation. We're going to apply that transformation there. Let's go ahead and plot the results. So now we've transformed our single feature, or latitude feature. So this really should be this transformed. So this is the transform latitude value. So now we see, okay, if we were to draw a line, it's going to do a better job than we had before. Okay, so let's import our function, do a train test split. Let's shuffle the data. Let's go ahead and train our regressor with the training set, make predictions. Let's go and compare it with another machine learning model, one that's going to be that can capture this nonlinear behavior that we saw before. So what's going to happen here, we're going to compare how well the linear regression works with the transform feature with a decision tree model using the untransformed feature. So fit and train the model. Let's go ahead and plot the results. We'll do that right there. So we have here in orange is the result of the linear regression model, and in green is the result of the decision tree model. So notice, if we look at the mean squared error, they're about comparable. So we see here we can go ahead and engineer a feature, apply a transformation to help out linear regression because it's a simpler model. And now we can argue that either one does just as well, and perhaps we want to use a linear regression model because it's easier to derive insight and to understand how the model works. Although decision trees are also easier to understand, but the point here is sometimes it works, it helps out to plot the behaviors and see if there's a way you can generate linear features, just like we did here, to help out some of those simpler models.